Right. Hello and welcome to Calculus 1. We are going to start with our 2.2 section. We're going to go through basic concepts of limits and see what they are. The definition, ironically, is all the way at the end of the chapter in 2.7. So we're going to cover everything about limits, properties, and the way to compute them, and what they're used for, even continuity, and then we're going to define, which is fine, because that's exactly the way it was discovered in the past. Newton used limits, didn't know what they were. A lot of people for 100 years used limits without proper definition, and then in 1850, Weierstrass defined limits. So we're going to pretty much do the same, learn everything about limits and then define them at the end. All right, so what is the street definition of a limit, right? Well, limits are used to compute y value of the function. Limits compute y value of the function. It's pretty much the same like regular computing value of the function, but they can do a little bit more. They're a little bit more powerful than computing the value of the function, and they do have one drawback. So we'll see where computing the function is necessary, and we'll see where limits can actually help us, where function would not be able to do what we need. But before that, let's just write that limits compute y value of the function. Guys, this is a street definition of it, right? So if you are to, I don't know, pull a stranger on the street aside and just say, okay, so what is the limit? This is what would be the word on the street. The proper definition is in 2.7. So we have the notation as the limit of f of x as x approaches some value a will give us a value L. So this is the notation for the limit, and the way to read this is limit of f of x as x approaches a is L. So that's the way to read the limit. And now what do we get from this? Well, what is the limit? We said it computes the value. It computes the y value, but it computes it differently than the function does. See, the function computes at x. So you have y equals x plus 3. And the graph for that is 1, 2, 3 y-intercept, and the slope is 1. So this is what we have. And let's say you want to compute the value at 2. So what is f of 2? Well, it's going to be 2 plus 3, and you're going to get 5. You can check that. Here's your 2. You will go up and over, and this value is 5, right? 1, 2, 3, 4, 5. So value is 5. You see graphically, and you know that 2 plus 3 is 5. So you have two ways of figuring out, right, using the function, two ways of figuring out that your output for this function is 5. Now, what do limits do? Well, in this case, limit of x plus 3 as x approaches 2 is what? Well, let's use limits appropriately to figure it out. Now, the limits are part of calculus, and calculus is study of change, study of motion. So you do not use calculus to compute static values. You use calculus to compute systems that evolve. That's why it's used for all the physics and everything else. Things evolve in time, change with time, so we have derivatives, and then that gives rise to differential equations. So, how do we deal with this problem using limits? So here is our same graph as before. Nothing has changed. We still have our 45-degree line that goes through number 3, and we still want to figure out what's happening at 2. Now, what I'm going to do is I'm going to use the limits this way. I'm going to first draw this line here, even though that is the pre-calculus solution through functions. Here's what I'm going to do first. Guys, do you see that this arrow x goes to 2? So what are the ways for us to go to 2? Well, you can approach 2 from left or from right. And I call those approaches Romeo and Juliet. All right, so we have a Romeo. I don't know if you know the story, right? It's an old story, Romeo and Juliet, about stupid teenagers. So yeah, you should look it up. So here you go. You're approaching 2. That literally means you are walking on the x-axis, approaching number 2. That motion translates on the function walking up the line, which in fact translates into a motion walking up the y-axis. And that's the right. So that's the motion for approach from the left. Let's say it's blue approach, and if you are looking at the picture here, you see that as you are approaching 2 on x, the blue arrow approaches 5 on the y, right? And now you take a look at the left, and then you go down. So this is approach from the right, which is the red, which is a Juliet approach, right? And then you go. So this is the greatest stereotype of all time: blue for the boy and red for the girl, right? Yeah. So here you go. You approach from the left, you approach from the right, and as you can see, they meet at 5, right? They meet at 5. So approach from the left, approach from the right, those motions translate on these, and then they would meet at 5, and then they kill themselves. So now, what do we do next? We can explore this using the chart. You are approaching 2 from the left and from the right. Now, what are the numbers smaller than 2 that are always getting closer to 2? 1.9, 1.99 is closer, 1.99 is closer still, right? So those are all the numbers that are smaller than, right? So these are your, well, let's put, it doesn't matter, X and a Y, doesn't matter which one is which. And then on the other side, right, you want to be closer and closer and closer. So 2.1, 2.01, 2.001, right, is always closer to 2 as you are approaching from the right. So here is the left approach, and here is the right approach. Now, you can compute these values and see what they get. So what are the blue values? Well, 1.9 plus 3 is 4.9, then 4.99, then 4.999. So where is the Romeo going? To which value? If you look at the blue numbers, right, they're approaching number 5. So Romeo is approaching 5. Now what's happening on the Juliet side over here? 2 plus 3 is 5.1, then 5.01, then 5.001 when you compute, right? 3 plus 2.001 is 5.001. So where is the red one going? Red one is also going to 5, right? It's dropping down to 5. So you can see that the blue one is rising into 5. And look at the y-axis. Do you see that the blue arrow is going up towards 5? And the red arrow is dropping down to y equals 5. Now, since they both agree that they're both going to 5, they are going to meet at 5, right? If it walks like a duck and it quacks like a duck, it's a 5, right? So we get our answer to be 5. This is the way limits compute y value. You see, functions compute at the point. So function plugs in 2 and says 2 plus 3 is 5, and you get 2 plus 3 is 5. Limits compute infinite number of x values around the point, but never at the point. So limits are going to compute infinitely many x values before and after number 2, let's say, and they're going to infer that the answer is 5. And the function will compute just at 2 and nowhere else. So technically, when you put 2 of them together, they compute at every possible point around 2, including the 2. Now, you might say, why? if I already know the answer is 5, why would be computing infinitely many points? Well, hold on. There are functions that have holes. They have no values in there. And without the limit, you would never be able to compute the y values for the missing point. So the idea here is to provide a tool that you want to provide a tool that can compute the value differently, so you have more options for computing and more power over the situation. I can give you an example in what you would call real life, because this, what we're doing here, is a fake life. Think of a bridge that has a piece of it missing. So you have a bridge. Here's the river underneath, right? We can also put some support for the bridge, make it look like a bridge, right? So this one is what you would call, good enough C to pass the class, right? It's not 100%. It just works, right? See, the problem is that this bridge has a hole, and the car that drives this way, right in the water, right? So apparently 70% is not good, right? Bridge has to be at 100%, otherwise it doesn't work. Bridge doesn't work even at 97%. Bridge doesn't work. So how do you fix this? You will have to approach the problem from the left and from the right, right? And then you can fix the y value height that it's missing on the bridge. So when you look at these problems for limits and so on, you already have seen two ways of computing limits. One way is the graphical approach, and the other way is the table approach. And those approaches of computing many points and looking at the graphs will work 100% of the time. So let's take a look at some of the graphical approaches, some of the other approaches. So let's say that you have a quadratic function that touches at 2, and you ask, what is the limit of this function f of x as x goes to 2? Well, you will look as you approach from the left and as you approach from the right. As you approach from the right, you are dropping down to 0. As you are approaching from the left, you are dropping down to 0. They are both agreeing from both sides that the answer is 0. Remember, your answer has to be a y value, a number. So 0, 0, 2, 0 is a point on the graph. And we can see that as we approach 2 from the left and from the right, both of our y values are dropping down to 0, and the answer of the whole thing is 0. Let's take a look at a piecewise function. This is called a piecewise function, and it has two pieces. It has a piece that is a constant piece, and then it has a linear piece. We can figure out what these functions are and blah, 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 but now we just want to know what's happening at 3. What is the limit of the function as x approaches 3? Or let's call this g of x. See, that's exactly what we are going to talk about, the question you asked. So, what happens when I approach from the left? When I approach from the left, I am getting this value. Let's call that 1. So limit of g of x when I approach 3 from the left. I need to also, I didn't say it before, I should have, that notation for approach from the left is this little minus that you put like the exponent of 3. I'm going to write that after this. And the answer for that is 1. And now you have the blue approach from the right, which is limit x goes to the 3 plus of g of x, and let's say that gives us a 2, because you can see that we are falling down into 2. So when you look at these, they have a different value, right? They don't give you the same location. One is going to 1, the other one is going to 2, and when they don't have the same value, we say limit does not exist. Very good. Limit does not exist. We can just say DNE. So what we have here is when they both meet at the same value, that's the limit, that's the number. When they have different values, limit does not exist. So let's take a look at the notation here. So when I write limit f of x as x approaches a minus, this is approach from the left. And I'm just going to point with, I guess, blue into that minus. Then I write limit f of x as x goes to a plus, approach from the right. And I'll point into the plus. Okay. Now we get the first theorem of our course. Okay, before we do the theorem, here comes a very cool question. So if I write without minus and plus, then that's both approaches at the same time. And that approach breaks down into 2 of these, which the theorem that I wanted to write addresses. But I'm going to add to this now. Limit x goes to a, f of x, both directions. All right, so now we can write that theorem, and that theorem will just help with this question as well. The theorem says if limit x approaches a from the left of f of x is the same as the limit f of x as x approaches a from the right equals to some value L, then overall limit of f of x equals L. Otherwise, limit does not exist. This is insanely important, will be especially important later in a course. So, limit exists only when left limit equals the right limit, and it's always the same value. If the left limit is different than the right limit, right approach, then limit does not exist. And that's, believe it or not, that's it on limits. That's actually the entire chapter or the concept of limit forever. But then we have really cute uses for limits. So we kind of make things a little bit more interesting and easy. But you acquired all of the knowledge there is on limits by now. You can look at the graph, and if that's not clear, you can compute the values in a chart. Remember, you are not allowed to compute at value A, because that's what the pre-calculus does. You compute infinitely many values to the left and to the right, and if they are all pointing towards the same number, that's the limit of the function. That's the y value of the function. Now, computing the limit and computing the y value is not always the same, because functions could have dislocated points. I'm going to go back to the bridge, right? Where is this missing piece from the bridge? It's right here, right? It's in the water. It's dislocated, right? So this part is your f of a, which is your pre-calculus. This part here is limit f of x as x approaches a. As you can see, they're not the same value, right? So pre-calculus and calculus could agree, like they did before, right? That both give you 5. In this case, they both give you 5. In this case here, they both give you 0, whether you do pre-calculus or limits, which is calculus. But they do not agree in this example. They don't agree in this piecewise function because your limit does not exist. The function value at 3 is 2. It's right here where this dot is, where the closed value is. So they are not necessarily the same. Let's take a look at another example. Here is a function over here, n of x. Doesn't really matter what's the name of the function. And this value is here. Actually, you know what I'm going to do? I'm going to take this piece and drop it down. Like that. So this is going to be my, let's pick this value here as well. So let's pick that as A, pick this as B, and pick this as C. So now, what are we going to do here with the limits? Let's check. First, I'm going to take a look at the limit of n of x as x approaches a. What is the value there? Well, we see that this value here, right, is going to give me some value. Let's call that value, well, we should call it n of a, because that's what it is. It's whatever the y value is computing. But let's call it y1. So that gives us y1. There is nothing special happening here. You can use limits, you can use pre-calculus to compute this, right? If you had the value in terms of the equation for n of x, you can compute all of that stuff. They're the same. The interesting stuff happens when you look at this case. What is the limit as x goes to b of n of x? So that's going to be this value, this open circle here. Call that y2. So remember, you approach from the left, you approach from the right. They're agreeing that they should stop in this height, because that's where you traveled on your function, right? Left and right, one should be blue, one should be red, but whatever. They both walk on the line, and then they meet at the common y height, and that's the limit for the function. But where is f of b? F of b is where the black dot is. Call that y3. And as you can see, y2 is not the same as y3. So limits and pre-calculus are not necessarily going to give you the same answer every time, because the function value might be dislocated somewhere else, just like that piece of a bridge that ended up in a river, right? So naturally, there is a gap in the bridge. The car will not drive over that empty space. The car is going to drop right down into the river, and it's going to end up on the top of the missing piece. You see? F of x, the function, right, is at work right there, because the car is trying to be at the point at the all times, right? And we use limits to approach from the left and from the right to fix the problem, to patch that hole. And finally, we have the situation over here where we ask about the limit of x approaching c of n of x, and we see it does not exist, right? That's what we had before, because your function from the left is going to be on top, the function from the right is going to be on the bottom. They do not match the same y value, therefore by the theorem before, they don't agree, therefore no limit. But is there f of c? Yes, there is f of c. This black dot here will produce y4 value, and we do have this one. Can we have a situation where pre-calculus doesn't work? Sure. As I said, the value that doesn't exist. What if someone stole a piece of the bridge? So piece of the bridge is not in the water. It's just missing, right? Over the night, some trolls showed up and just like ate through the, through the portion of the bridge. So it's not in the water any longer. It's just nowhere. So you just have a discontinuity, a hole in the graph. In that case, pre-calculus cannot compute, because remember, pre-calculus computes at the point. The point doesn't exist. And what the limit does? Limit computes everywhere around the point except at the point. So limit has the great advantage there because the limit can compute the y value of the missing point. That's why we can actually fix the bridge, because we are able to approach the problem from the left and right and patch the hole, right? Where pre-calculus cannot do that. Pre-calculus just says, yeah, it's missing. That's it. Like, walk away. Nothing we can do. So I think that this picture sums up a lot of what limits are and what they do and how they're different than the pre-calculus just plug in and go in terms of that. So that's intro to limit 2.2. We learned that we need a left and right approach. We learned the theorem that when those two approaches meet at the same value, you have the limit. We also learned that we can do the chart of values. That works all the time. And we learned these what are called one-sided limits, approach from the left, approach from the right, to tell us what's happening. So now, before we, even though this will be repeated, I believe in 2.5 or whatever the name is, just want to mention, because you might run into some homework questions, let's just put e to the x function here. We're going to take a look at limit as x approaches negative infinity of e to the x. We're going to take a look at the limit x approaching 0. And we're going to take a limit as x approaches infinity. And after this, I'll do one more quick example and we're done with 2.2. We'll hit the break. So when you take a look at the first one, let's be red on it. This is what you're talking about. It is a one-sided limit where x goes to negative infinity, and the answer is 0. Because as x goes to negative infinity, this line, the graph, right, will keep falling and falling and falling towards the x-axis without touching it and crossing it. It will keep falling and getting closer and closer and closer. At infinity becomes 0. Now that infinity, we never reach it, but at infinity, the limit will be 0. So you need to extend this in your mind all the way to the left and say, as I am walking on this graph is getting closer and closer and closer to x-axis, and at infinity it will be at 0. Now, what's happening in the middle from the 0? Well, we approach from the left, we approach from the right, and they both agree at 1. Because the left approach was going up towards the 1, the right approach was dropping down on the y value into the 1, and together they reached, from both sides at the same time, they reached 1. So left limit 0 minus gave us 1, right limit 0 plus gave us 1, so combined together it gave us just 1 because they both meet, they both reach the same value. And finally, the last one is infinity, obviously, because as you go forever to the right towards infinity, you see that this one goes up forever towards infinity, so that one would be infinity. Now, these guys will be covered again twice. We will have infinite limits and limits at infinity, so we'll cover these limits again, so you don't have to stress. But there is one that you might want to stress about right now, and that's this one, 1 over x. So what is the limit as x approaches 0? for 1 over x. So when you have problems like this, breaking the problem down into the left approach and right approach is what you actually need. So you have your left approach, the Juliet approach, and you can see that Juliet is dropping down to infinity over here, as she did. So limit x goes to 0 minus of 1 over x is going to be negative infinity. That's what's happening to your y value. It's going down. And then we have the approach from the right, and that one is a Romeo, and that one goes forever up. So that's your limit. X goes to infinity, s goes to 0 plus. So we are approaching value of 0 on x-axis from the right of 1 over x is positive infinity. So the overall limit does not exist. They don't agree, right? So when I said stupid teenagers, they're infinitely apart, right? They are infinitely apart. And that's the end of the story. That's the end of the 2.2. It's tragic, but hey, it's calculus. So we are going to resume exactly at 12 with 2.3. For the one above, x goes to negative. No, we don't need a superscript for those because you can only approach infinity from one side, depending on which infinity you're looking at. So negative infinity approaches only from the right. You cannot approach negative infinity from the left because there is nothing before it, right? It's as meaningless as asking what's before Big Bang or what's south of a South Pole. So that's pretty much the same. You can only approach positive infinity from the left and negative infinity from the right. That's it. Great. All right, so see you exactly at 12 with 2.3.